العالمين.
All right, a few final building blocks for the day. So we started by talking about those command line arguments that Clang uses, whereby anything after the command that you type at a prompt, be it make or clang or even cd in Linux, any word thereafter or something cryptic like -o is a command line argument. It's an input to the command. It's different from a function argument because a function argument, of course, is an input to a function. But it's the same idea. It's just different syntax after the $sign at the prompt. Well, it turns out that command line arguments are something you can now use in your own programs by accessing words after the prompt. And let me propose that we invent this as follows. Let me propose that we switch back to VS Code here. And I'll open a new file here called greet.c. So in greet.c is going to be a program that very simply greets the user. Had we written this last week, we would have done this. Include cs50.h, and then include standardio.h, and then int main void. And then we might do something simple like string name equals get string, quote unquote, what's your name question mark. And then we would have printed out, as always, hello, comma, %s, and then plugging in that name. So this is the same program we've implemented many times just to make sure it works. Although, nope, that's not quite the same program. Semicolon's in the wrong place. This now is the same program. So make greet /greet, and I'll type in my own name, hello, David. So we're back there. Now, what's arguably a little annoying about this program, if I type in something else like Carter, enter, I have to run the program, wait for the prompt, type in my name, hit enter. And that's fine. But imagine if every program worked like this, like make. Suppose you could only type make. Then you wait for a prompt. Then you type the name of the program you want to make. Then you hit enter. Or worse, in Linux, when you have to change directories, as you might have for problem set 1, what if you had to type cd, enter? Now type the name of the folder you want to change into, enter. I mean, it just slows life down. And so it just gets annoying quickly. So command line arguments just let you express your whole thought all at once. So how can I do this? Well, if I want to express the notion of command line arguments in my code, I could do something like this. I could, for the very first time, go up and get rid of this void, which as of today means this program takes no command line arguments. And I can change it to exactly this. Int argc string argv with brackets. Now, it's cryptic, admittedly, and let me zoom in. But I think we can perhaps infer now what's going on. If main now does not have void as its input, which means it takes no arguments, surely the spoiler here is that now main will take command line arguments somehow. Any guesses as to what argv is or will be? What might this represent? It's an array of strings, right, by way of the syntax. Yeah? Exactly. It will be all of the characters, or really all of the words that you type at the prompt. argc as an int, any guess? Argument count is what it generally stands for, though technically you could call these things anything. But this is the convention. Because I claimed earlier that arrays don't keep track of their own length, if you want to know how many words the human typed at the prompt after your program's name, you have to be told not just the array of the words, but the length of that array. The strings you can figure out the length of using strlang, but you can't figure out the length of the array of strings, the collection of words that the human typed in. So how can I now use this? Well, let me go ahead and do this. Let me go ahead and change this program now just to be printf, quote unquote, hello, comma, %s \n, then argv bracket 1. So this is not the best version of my code yet, but it's my first. Make greet. And now let me do /greet David all at once. Enter. Hello, David. Now let me run it again. /greet Carter. Enter. Hello, Carter. It's a marginal improvement, but I don't have to wait for getString to prompt me to hit enter. It's just speeding things up, twice as fast. One less command to type in. But I deliberately did bracket 1. But what's the beginning of argv? It would be bracket 0. Well, what's that? This is sometimes useful, though for now it's not. Suppose I recompile my code and run this program now, greet David, Anyone want to guess what's in argv0? Say again? Greet. Enter hello./greet. So if you want, sort of Inception style, your program to figure out what its own name is, or at least how it was executed at the command line, at the terminal, you can look at argv0. In general, probably not that useful. Probably better to start looking at bracket 1, which was the first word after the program name. And if there were more, I could do this. How about argv bracket 2? Let me add in a second %s. Let me recompile greet. Let me do /greet David Malin, enter. And that too now works, taking in 2 words at the prompt. If I really want to be smart at this now, I could do something like this, though. How about if the count of arguments, aka argc, equals 2, then assume that the human typed in only their first name, and do printf hello, comma, %s, \n, and then argv bracket 1. Else, if the human did not provide exactly 2 arguments, the name of the program and their own name, let's just print out a default value, lest they forgot their name or they typed in 2 names or 3 names. Let's just do hello, comma, world as a default, and we'll just ignore what the human typed in. If I recompile this, make greet, I can do /greet and David again, enter. Oops. Sorry, what am I missing? Yeah, so newbie mistake. Else. All right, make greet again, /greet David, enter. There's my hello David. But if I omit my name, I just get the generic, like a default value. And if I get a little curious and I type in both names, then I get ignored too. Why? Because I just haven't built in support for argc of 3. I could do anything I want, but now we have access to these kinds of building blocks. All right, what else might I do here? Well, it turns out there might be some final features for us to now execute. Notice, though, that in C, despite what you might see in books or online tutorials, nowadays, the 2 official formats for defining a main function are either this, which we've been using now for 2+ weeks, or now this, whereby you change the void to int argc, and then for now, string argv, and then empty brackets. And we'll see that this too is a simplification, some training wheels, if you will. But for now, those are the 2 forms. Even though you will see in online tutorials and even books, some people use main in different ways. These are the 2 now to keep in mind. And I'll note that these command line arguments are kind of all over the place. Didn't probably expect to see this word on the screen here. And what does it mean? Well, it turns out that for decades, there's actually this program that comes with Linux systems in particular called cowsay. Why? Probably because someone had too much free time once and decided to write a program that creates ASCII art out of a cow saying something textually on the screen. But you use cowsay, just for fun, by way of command line arguments. So for instance, let me propose that I go back to VS Code here, not because I want to write any code, but I just want to use my terminal window. And let me maximize my terminal window here. And let me go ahead and type in something like, how about cowsay space moo. So cowsay is not a program I wrote. It's been around for decades, but we installed it in VS Code for you in the cloud. It takes at least 1 command line argument. What do you want the cow to say? I can say cowsay moo and hit enter. And voila, there's my ASCII art of a cow saying moo on the screen. It can say multiple words. So I can say hello world, enter. And now it says hello world. So this is just an example of a silly program that uses command line arguments, but it takes others too. Just like Clang used this convention of hyphens to change the output of the program, dash something is just a super common convention with command line arguments when you want a very terse notation for some option, like output. In cowsay, I read the documentation, and it turns out there's a -f command line argument that allows you to change the appearance of the cow, if you will. So if I do cowsay -f duck, and then some other word like quack, it's no longer a cow. That command line argument turns it into a tiny, adorable duck instead. And then lastly, just for fun, because I spent way too much time playing with command line arguments, cowsay -f dragon, and then how about like rar, enter. You can even get this on the screen here. So this too is just an example of what you can do with these command line arguments now that we have this building block. And there's one final thing we can now do with code. There's one last feature today that we'll introduce before we now connect all of these dots to readability and encryption by talking lastly about something called exit status. It turns out that whenever your main function exits, it returns a secret integer that you can figure out as the programmer or an advanced user what it was. And these exit codes, exit statuses, are typically used to indicate errors. So for instance, over the past couple of years, if you've used Zoom and you ever got some kind of error, you might have seen a screen like this. It's usually not that helpful. Maybe tells you to click report problem or contact support. But very often in our human world on Macs, PCs, and phones, you see cryptic error codes, like literally numbers that probably only Zoom knows, or Microsoft, or Google, or whatever company wrote the software you're using. But that number corresponds to a specific error that some human somewhere knows might very well happen. These are used similarly, although under a different name that we'll talk about later in the term, on the web as well. Have you ever seen this, maybe not character, but number? So 404 means what? So error, yes, but really not found. So why? I mean, this is the most arcane thing, and we'll talk in a few weeks about like what this and other numbers mean. But numbers are all around us in technology, and they very often mean something to the technical people who wrote the software, less so to humans like you and me. Why so many of us recognize 404 is kind of weird, that like that's been around long enough that we all know it, but it really is just a special number that represents an error of some sort. So it turns out the last thing we'll reveal today about what we've been taking for granted for 2 weeks is what the int is in main. We've seen just a moment ago that the thing in the parentheses, which up until now has been void, which means no command line arguments, now int argc string argv brackets just means yes, command line arguments. And we've seen how to access them. So the last piece of the puzzle, honestly, of all the cryptic syntax the past 2 weeks, is just what int means. And in fact, you don't need to use command line arguments to have this discussion. So let me revert to the simpler form. Int is always there for main, and it indicates that main will always return an integer, even though you and I have never done so explicitly. Usually, main returns 0 by default. But it would be weird if you saw an error message saying 0. So 0 is just hidden. You would never see it on the screen. But it's happening automatically by way of how C is designed. So let me write one final program here. I'll call it, for instance, status.c to show you these exit statuses. Code of status.c. And then up here, let me do something simple like include cs50.h, then include standardio.h, and then int main. Let's use a command line argument. Int argc string argv. So that's copy paste. But now let's do this. If argc does not equal 2, why don't we do something like this? Let's not just default to hello world like last time. Let's yell at the user. So let's say something like printf missing command line argument, so that they know they screwed up and they need to run the program again correctly. Else, let's go ahead and say print out, as before, hello, comma, %s, and then plug in argv bracket 1, so the human's name from the prompt. Now at this point, let me go ahead and run status, /status, and I'll type nothing first. I get yelled at. This time I'll type it again, /status David, and it works properly. But now let me show you a somewhat secret cryptic command. You can type this at your prompt, and it's just a coincidence that there's another $. Echo $? Totally arcane, but it allows you to see what exit status your program has ended with. So let me run this again the wrong way. /status. OK, I get the error message. What was secretly returned? I can't see it. There's obviously no error screen. But by typing echo $? I can see that, oh, my program automatically, by default, returns 0. However, if I run it again correctly, /status David, enter, this is the correct version. But if I run echo $status again, it's still entered with 0. And long story short, this is just a missed opportunity. When something goes wrong, why don't I return a value other than 0? 0 by default means success, and it's always there automatically. But you can control this. I can go into my code here and return 1 or 2 or 3, or what was it in Zoom? I could even return 1132 just because Zoom did that too. Else, if something works fine, I can return 0 by default. And honestly, if I omit the return 0, again, 0 automatically is returned. So let me go ahead and though be explicit, just so I know what's going on. Make status again, /status. And let's do this correctly with David. Enter. Hello, David. Echo $? 0. So all is well. But now if I do /status and nothing, or multiple things, but not just David, enter, I get the error message. But now if I do echo $question mark, oh, damn it. I shouldn't have chosen 1132. Let me cheat. Pretend that didn't happen. I'll explain sometime. /status without anything, enter. We indeed see the error message, echo $question mark. Voila, there now is the 1. So I used too big of a number. This is, I'm going to surmise it's only using 8 bits, even though we called it an int, which means we were overflowing the 8 bits. And that's why 1132 suddenly became much smaller. But I'll double check that to be sure. This is why I shouldn't go off script. So what does this now mean? This is, in the graphical world, we would just show something like this on the screen, which is a little more informative to the user. But even in the Linux world, where you don't have a GUI necessarily, even for the programs we've written, you can check these exit statuses. And in fact, more comfortable, more advanced programmers, when they write code that calls programs, be it cowsay or anything else, you can encode, check what the exit status is of a program, and then decide, did my program work or did it not? So if you go on to do things in data science or in general analyzing data, writing scripts, writing programs to analyze data, it's just very useful to be able to check programmatically with a command like echo $question mark, weird as it looks, did my program succeed or did it not, even without seeing something user-friendly or graphical or textual on the screen. And now let's connect the final dots before we adjourn for some fruit snacks. Cryptography, namely one of the applications this week via which you'll be able to send, if you will, secret messages, and better yet, decrypt secret messages. This will be in addition to perhaps analyzing the readability of text using heuristics, like we identified at the start of class 2. So cryptography is just the art, the science of encrypting information, scrambling information, so that if you have a secret message to send in so-called plain text, you can run it through some algorithm and turn it into what's called ciphertext, thereby encrypting it. And only someone who knows what algorithm you've used and what input you've used to the algorithm, theoretically, can decrypt that process and convert it back to the original message. So if we use our mental model from last week, here is a problem. Here is an input and output. The goal, I claim here, is to take some plain text, like the message you want to send. Think back to grade school. If you ever passed a note to a friend or to your crush saying, I love you, it's a little awkward if the teacher or someone else intercepts the paper, and in English it just says, I love you, or whatever it is. It'd be nice if you had at least encrypted it in some way. But the other person needs to know what algorithm you used and what inputs you used to that algorithm, so that ultimately they can decode the so-called ciphertext, which is the output. So what goes inside of the box today? Well, an algorithm, as it relates to cryptography, is called a cipher. And a cipher is a fancy name for an algorithm that encrypts text, from plain text to ciphertext. The catch is, there needs to be not just the algorithm, there needs to be an input to it. And so, for instance, you might draw the picture like this for the first time today. And we've seen this in code. You can give multiple inputs or arguments to functions. So in this black box, can you imagine passing in the message you want to send and then some secret? So for instance, suppose that the simplest thing I could think of as a kid was, instead of sending the letter A, why don't I write the letter B? Instead of the letter B, why don't I write the letter C? So I can kind of shift the English alphabet by one space. So A becomes B, B becomes C, ... Z becomes A. You can wrap around at the end. And let's assume no punctuation in this part of the story. So that's a very simple algorithm. Add a value to each letter and send the value as the ciphertext. And now the teacher, the classmate, they have to know that you use not only this rotational algorithm, also known as a Caesar cipher, they also need to know what number you use. Did you add 1 to every letter, 2 to every letter, 25 to every letter? Now, if they're super smart, and probably not the young age in this story, they could also just try all possibilities. And that would be an attack on the algorithm. This is not a sophisticated algorithm. But it's enough to send a message in class. So if the two inputs now are hi as the plain text message, and 1 as the so-called key, the secret number that only you and the other person know, you might be able to encrypt a message from one way to the other. And so in this case, for instance, hi would become IJ! Exclamation point. In this version of the algorithm, we're not going to bother with numbers or punctuation. We'll only operate on A through Z, be it uppercase or lowercase. So now if you were to receive a slip of paper in class with IJ on it, you know, you, the recipient, would know what it is so long as you know that the sender used 1, because you just reverse the algorithm and you subtract 1 instead. The teacher, you know, they probably don't know what this means, and they're not going to spend time hacking the message, so it just looks scrambled to them. And that's what we get from encryption. Someone who intercepts it, be it in class or in the real world, on the internet or anywhere else, can't actually figure out, ideally, what it is you have sent. The opposite, of course, is indeed called decryption, but the process is the same. We now pass in -1. And so how about this? Why don't we end with a demonstration here? UYJTXBTDT50. There's a bit of a tell there. If we pass that in and do -1, well, how do we get out the plain text originally? Well, if this is the ciphertext and we subtract 1 from each letter, I think U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, B becomes A, T becomes S, D becomes C, T becomes S. And this was indeed C is 50. Have a duck on your way out and some snacks in the lobby.